Let's start the class. So today we will continue to see the example of Burnside's theorem, and we will prove it, why it is correct. Okay, so this is for the preparation of the proof. So let's skip this for now. Let me first talk about this problem. Okay, so suppose that we have a p polygon, p-sided polygon. So 1, 2, 3, 4, 5, 6, 7. Okay, so regular polygon. Yeah, it may not look regular, so make it more regular. Okay, so let me see. So I have 1 here, I would have 1 here, 1 here, and then I will have 1 here, 1 here, and then I will have 1 here, and then 1 here, and then I will have. Okay, so let's say this is a regular polygon. This is a p-sided polygon. And then p is a prime. So for instance, in my example here, p is equal to 7. Okay? Now suppose that each vertex can be colored. Okay. Each vertex can be colored in one of the A colors. Each vertex can be colored or in one of the C colors. In one of the C colors. Okay? And then okay, and then we assume that 2 configurations are the same, so 2 colorings are the same if they are the same after rotation, are equal if and only if they are equal after some rotation. Okay, so as before, we want to count how many different configurations can we have. So if they are all in the same color, this is one of the color, right? And then if they are all in the black, this is also one color, right? And then we want to ask how many configurations are the same. So how should we do? Okay, so we want to count the number of classes using Burnside. So the number of classes or the number of distinct configurations that we can look at is equal to what? Is equal to the sum of all invariants in all the possible rotations that we can imagine. Does that make sense? So let's say we look at this G to represent different kinds of rotations. So not rotate at all, rotates by 2 pi over 7, rotates by 4 pi over 7, and so on and so forth. Is that okay? So for each different rotation, it corresponds to some kind of a permutation of the elements. Is that okay? Okay. And then we consider all the 7 possible rotations that we can have. And then if we count the total number of fixed points, the total number of invariants in each of the cases, add them together, divided by 7, then this will be the number of classes that we want to show in our example. Is that okay? Okay, so let's say, so how many are there? So how many are there? So the number of equivalent classes. So how many are there? So first of all, in general, there are going to be p rotations that we need to take care of. Is that okay? And then the first one is we don't move at all. We don't move at all. So each of the coloring will map to itself after the permutation. Does that make sense? So in that case, for that particular case, for the pi that corresponds to no rotation at all, how many invariants do we have? How many? Each vertex you can calculate in one of the C colors. So how many are there? C to the power P, am I correct? Is that okay? Okay. So C to the power P. Is that okay? This corresponds to no rotation at all. Now, suppose that we have a certain coloring of this, and after rotating by 2 pi, is it 2 pi? Yeah. After rotating it by 2 pi over 7, it is the same. Then what does that mean? So we color it, and then we rotate it by 2 pi over 7, and it's the same. What does that mean? It means that they must all be equal. Am I correct? Is that okay? Okay, in general, if this is a prime, if it is a prime, or whether it is a prime or not, you rotate it by just one vertex, and it is going to be the same, then it happens if and only if all the vertices are in the same color. Is that okay? So in that particular rotation, there are going to be C invariants. Is that okay? It is all black, or all white, or all blue, or all yellow. One of the C of them. Is that okay? Now this is rotating by just one vertex. So if we rotate it by 2 vertices to the right, and it needs to be the same, then it means that this one and this one has the same color. This one and this one has the same color. This one and this one has the same color. This one and this one has the same color. This one and this one has the same color, and this one and this one has the same color. Am I correct? Then in that case, there are only C of them. In general, if it is a polygon with P vertices, so if it is a polygon with prime number of vertices, we see that 2 is a generator. 2 plus 2 plus 2 plus 2 plus 2 will generate the whole set. Because 2 is not the identity. Okay, it is not 0. It is not the identity. Each prime number, each group of prime number, 0 up to p minus 1, with the operator plus modulo p, it is a cyclic group, and it has only one generator. The 0 is the 1 is the, no, sorry, not one generator. It has p minus 1 generator. Everything except the identity are generators. So in that case, if you have 2, 2, 2, 2, 2, 2, 2, then you generate the whole group, which means that all the vertices has to be the same color. And similarly, if you look at this, if we rotate it by 3 vertices, so it also implies that all of them has to be in the same color, because this one has to be the same as this one the same as this one, 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 this one the same as this one. Is that okay? Is that okay? So in that case, you also, it is going to be plus C, plus C, plus C, plus C. And then all together, there are p minus 1 of them. Is that okay? So if we write it down, so it is going to be C to the power P plus P minus 1 C divided by P. If you are okay with this so far, could you please raise your hand? Okay, excellent. And then this is a proof. This is going to be a proof of the Fermat's little theorem, an alternative proof. So why? So assuming that Burnside is correct, then this is a counting of the number of classes, which is an integer. This has to be some integer, some natural number, right? Right? So what does that mean? So it means that C to the power P plus P minus 1 C is a multiple of P. Otherwise, it will not be an integer after dividing it by p. Is that okay? So this implies what? Because this is modulo p, p minus 1 is the same as minus 1. So you put this on the right-hand side. So this implies c to the power p is equal to c mod p. Is that okay? So this is Fermat's little theorem. So if Burnside is correct, then Fermat's little theorem is also correct. Is that okay? Okay, good. Yeah, I think this is interesting. Yeah, let's see one more example. So this time, let's look at the 5-digit number. So each number, we assume that it is written in this way. 1 is like this. So that it is the same if we look at it upside down. 2 is like this. So it is not the same as if it is looking upside down. 3 is like this. 4 is like this. 5 is like this. 6 is like this. 7 is like this. Okay. 8 is like this. So that 8 looks the same upside down. Is that okay? 9 is like this. So if you put 9 upside down, it becomes 6. So not upside down, sorry. I mean like this, rotation. So if you have a plate like this. So let's say you are going to write down this a 5-digit number. Let me write down 0 in a plate. So let's say I have 1, 0, 6, 0, 8. So this is a plate, right? So we can somehow, let's say the plate is dropped on the floor. Then in that case, when you put it up again, you may read it the same as like this, or you may read it like this one. Okay, so the 8 is here, 0, and then 6 becomes 9, 0, 1. Is that okay? Okay, is that okay? Okay, so in that sense, we are going to say that this plate and this plate are equivalent because one can be transformed into the other by doing this kind of rotation. Is that okay? This kind of rotation. Okay? Now, the question here is that suppose that we have the license plate, so these are the license plate for cars, that has 5 digits. How many distinct license plates can we get? So we don't want to have a plate for this one and a plate for this one because these two are considered equal. They're the same. Okay. So if we have a plate like this, we should not have a plate like this. Is that okay? Is that okay? So how should we solve this problem using Burnside? Okay, so in that case, so for instance, let's say this is the so-called rotate operation. So suppose that we have something like this, 1, 2, 3, 4, 5. Let's say we have something like this. Then if we pick it up and rotate upside down on this way, then there's nothing that you can do. Okay, so we will still, it does not have any other thing that maps to itself. That maps to it. So we will still consider it as 1, 2, 3, 4, 5. Is that okay? Because there is no way that you can look at it in another way. Okay, so they are the same. Okay. But for this one, if I start with this one, then I do the rotation like this, then it becomes this one. Okay. So Burnside. So using Burnside, it will be very easy. Okay. So we will consider a set S of how many items? So of 10 to the power 5 license plates. Is that okay? And then we will consider G of S that represents what? There are going to be 2 permutations here. One means that no rotation. and then this one is rotate by 180 degrees. Is that okay? Is that okay? So it's like rotation by 180 degrees. So if we know how many invariants are there, and then how many invariants are there, then it's done. Because we add up the total number of invariants divided by 2. This will be the answer. Okay? So how many invariants here? So the number of invariants here is easy. Everything is invariant. So 10 to the power 5. Is that okay? How many invariants here? So you want to have invariant. Invariant. So this is not invariant, right? This is 10608. It maps to 80901. These two numbers are not the same, right? This is not an invariant. But if you have 11111, then it maps to 11111. Then it is an invariant. How about 10801? Is it going to be invariant? Yeah, this is going to be invariant. How about 10601? Is it going to be invariant? No. Okay, so this is not going to. So first of all, invariant, then you don't have much choice. The middle digit has to be what? There 108. There are only 3 choices. Okay, so they're invariant. So there are 3 choices for this middle digit. Is that okay? How many choices are there for this digit? Well, for this digit, at least you need this digit to, you can, well, okay. So there are, there are a lot of invariants actually. 1, 2, 3, 4, 5 is an invariant because 1, 2, 3, 4, 5 has to map back to 1, 2, 3, 4, 5. Okay, so somehow we need to differentiate things. Okay, one is all the digits are from this. So we need to consider 2 cases. Okay. Well, we need to consider 2 cases. One case is all the digits are from this set 0, 1, 5, 6, 6, 8, 9, and some digit is from the remaining set 2, 3, 4, 5, 7. Is that okay? So there are actually 2 cases we need to consider. These 2 combined, it gives us all the digits, all the 10 to the power 5 possible number places, right? Either you have all the digits chosen from this set, or if it is not this case, then some of the digit must have, some of the digit must be a 2 or a 3 or a 7 or 4 or 5, right? Okay, by default, any plate that contains a 2, 3, 4, 5, 7, you can read it without any problem. So it is going to be invariant, even after the rotation. Okay, so how many are there? How many are there? So it is going to be 10 to the power 5 minus 5 to the power 5. Am I correct? Does that make sense? Yeah, because these are 5 to the power 5. Is that okay? Is that okay? So these, okay, so all these are going to be invariant. All these are going to be invariant. But out of these 5 to the power 5, not every of them are invariant. Okay, if you want this to be invariant, then so we get back to this analysis. So the middle digit, you don't have much choice. It has to be a 0, a 1, or an 8. Okay, and for this one, it will have 5 choice. You can put it at any number. You can put a 0 here, a 1 here, 8 here, a 9 here, a 6 here. It's okay. But when this has 5 choice, then this will have only 1 choice, because this one and this one has to be the opposite of the other. Okay? Is that okay? If this is a 0, then this is a 0. This is a 6, this is going to be a 9. Is that okay? And similarly, there are 5 choices here, but then there was only 1 choice. Is that okay? So out of these you have only 75. Okay. So this, you have only 75 here. 3 times 5 times 5. Is that okay? Okay, so, so this one will be a little bit complicated. So this one, let's write down. So this is going to be 10 to the power 5 minus 5 to the power 5 plus 75. Is that okay? Okay, so the answer, the number of classes that we have is going to be, you add these two, you divide by 2. Okay, you add these two, so you get 10 to the power 5. And then 5 to the power 5, how large is this number? 5, 25, 125, 625, 3125. Okay, so you are going to minus 3125. And then you are going to add back 75. And then for this one, you need to divide it by 2. Is that okay? Yeah, so this is 30501525. Okay, so it's like this. Minus 1525. Is that okay? So if you calculate this, so it's going to be 8475. Is that okay? Something like this. Okay, my calculation may be wrong, but this is the idea how this can be solved. Okay? Okay? Is that okay? Good. Okay, now let's get to the proof. Okay, why this? Maybe not. 10 to the power 5. Yeah, you have one more digit. Sorry. Yes. Is it? Thanks. Okay. Good. Okay. I missed an important digit. Okay.